with Anna. I'm Anna. This video is about the experiment that proved the existence of the atomic nucleus. It's the third in a series. The other two videos are linked in the description below. One of them is a helpful overview if you're not familiar with the experiment. Basically what they did was they shot particles at a thin sheet of gold, and the particles flew off in various directions, and they analyzed the directions that they flew off in, and Rutherford, or his graduate student more likely, proved that the experimental data could only be explained if there was a solid core at the center of the atom, massive. The reason for that is because some of the particles bounced back 180 degrees opposite the direction they came in on, and that could only be explained if there was an atomic nucleus. You don't have to take notes from this video, because if you request it from me, I will send you the PDF with the equations. So basically, and the Wikipedia article explaining the analysis are very inadequate. They're complicated, there are steps missing, there are errors, many errors. And so I worked through the equations, but I found that I needed numbers, really. What I really needed was a laboratory where I could do the experiment. Now that's, of course, not available to me. So I simulated the experiment on my computer and got, I basically computed the path of the incoming particle as it approaches the nucleus and flies off at an angle. And I used that to verify the formulas that I derived. So here it is. What's this all about? Well, the story begins with atoms. They were thought of as particles, tiny point-like objects. This was the basis of chemistry, which was well understood at the time of the experiment, 1909. But folks had gotten curious about atoms and wondered if, when they looked at them more closely, they might have different parts. They might have parts or different constituents that made them up. This motivated Hans Geiger and Ernest Marsden to shoot a beam of alpha particles at a thin sheet of gold. Alpha particles are helium atoms that have lost their electrons, their ions. They're positively charged. So Geiger and Marsden recorded the angular distribution of the alpha particles as they come flying off. That is, they counted how many passed straight through, how many were slightly deflected, how many were more substantially deflected, and so on, putting numbers to the angles and counts. Here's a cloud chamber photograph of a more modern version. Here's a cloud chamber photograph of a more modern version of the experiment. They used a vapor, and they shot the alpha particles into the vapor, nitrogen or oxygen, something like that. Now, if you look closely here, you can see the alpha particle coming in from the lower right. Here it strikes the nucleus. Now, these nuclei are heavy. They're much heavier than the alpha particles, but they do recoil a little bit. So you can see this little blip right here where the nucleus recoiled. The alpha particle kind of kicked it. And here's the main point of interest, the path of the outgoing alpha particle. The quantity of interest is this angle right here, indicated by the Greek letter theta. That's what we're going to calculate. So here's a schematic diagram. The alpha particle comes in from the left here, comes close to the nucleus, and it's deflected off at an angle. Here's the angle, the scattering angle, theta, measured from this line, which is the direction of travel, the initial direction of travel of the alpha particle, measured from that line to this line, the direction of the outgoing alpha particle. And in this picture, it's about 50 degrees. One way to think about a hyperbola is to imagine a cone, like I've shown right here. And you slice it with a plane, and you slice it at an acute angle so that it doesn't cut all the way across to the other side. And this produces the shape that's known as a hyperbola. However, it's easier to look at it in terms of the two-dimensional picture. I should tell you, this whole problem is two-dimensional. The particle comes in, it's kind of going towards the nucleus, but not head-on. And so you have like a plane formed by the velocity of the alpha particle, its position, and the position of the nucleus. So that gives you three vectors that form a plane. The alpha particle doesn't move perpendicular to its, it doesn't change direction in three dimensions. It's a two-dimensional problem. It's in a plane. So here's the path right here. The green arc is the path of the alpha particle. It's a hyperbola. And the way a hyperbola is defined is you have 2 points, foci. One of them is the position of the nucleus, the target, the gold nucleus, and one of them is off at a distance from there. And the deal is if you take the distance of the alpha particle from one focus, and you take the distance from the other focus, and you subtract the shorter one from the longer one, then you get, well, in this picture you get 4, no matter where you are on the green arc, but you get a constant. So the difference between the distances of the particle to the 2 foci is constant. And I'll explain what that means when I do the math in a little while. So grinding through these formulas was a bit of a challenge. It's very hard to be sure when I'm going from the 7th step to the 8th step that I haven't made a mistake. Very hard to check the equations, and there are so many of them. So I needed numbers. I really needed to do the experiment in a laboratory. Well, that wasn't an option. I don't have a cyclotron or a particle accelerator. So I simulated it on a computer, basically. That's the brute force approach. You just look at it in Cartesian coordinates. That's X, Y, and Z. So it's all about the forces. Newton's second law of motion says that the acceleration, the rate of change of the velocity, that is the second derivative of the position with respect to time, the acceleration is proportional to the applied force. These are the forces put off by a gold nucleus. As you can see, they all point outward from the center where the nucleus is, and they're stronger close in, and they get weaker as you go out. It's an inverse square law. The figure says K over R. It's actually K over R squared, so that if you go twice as far out, the force is 4 times weaker. So I wrote a little 5-line Python script that gives you the force pointing outward from the nucleus. And it's in what are called Cartesian coordinates, x, y, and z, three perpendicular directions, which you can see here. The green is x, the blue is y, and the red is z. Now, the path is only in x and y. The alpha particle doesn't move in the z direction. But that's the way I simulated it. And I'll show you the code now. I use the library called SciPy to perform the integration. Here at the top you see the function getRates. It takes as input the position and velocity of the particle. It computes the acceleration, and it just returns the velocity and the acceleration. And then the library integrates it automatically, and you get better results than if you do it by hand. The main function for this is right here, SciPy Rutherford simulation. By trial and error, I got the initial energy and what's called the impact parameter, and the mass and speed of the incoming alpha particle. And I'll show you the impact parameter in a moment. And then I just call this library function solve IVP. I tell it where to get the velocity and acceleration. I tell it what time period to use. I give it the initial velocity and acceleration. And then it returns the position and velocity at various time points. So that's really all there is to it. To get the simulations started, you have to give what's called the impact parameter. And I've shown that in this figure here. This is the path the alpha particle would take if it were not charged, if there were no forces deflecting it. As you can see, if it just went in a straight line, that's Newton's first law of motion. When there's no forces, things move in a straight line. It would pass within a distance, this distance right here from the nucleus. This is called the impact parameter, and in this illustration it's equal to 0.2. Here are the results. I've just shown you a brief time interval when the alpha particle is very close to the nucleus. You can see where it reaches its point of closest approach. That's called the periapsis. And it is a hyperbola, as it is supposed to be. Now, the calculus method, the main point of this video is doing it with the equations rather than numerical simulation. It uses what are called polar coordinates, where instead of x and y, you have the radius, the distance between the two particles, and the angle from the x-axis to the position of the alpha particle. And I've shown that here. This is polar coordinates. And here's the transformation for polar coordinates. So the radius is computed by the Pythagorean theorem, so it's the square root of the sum of the distances in two perpendicular directions. It's a right triangle. This is the angle. It's computed by the arctangent function. That's the inverse function. And in Python and many other languages, it's called arctan2. The first argument is the vertical distance, and the second argument is the horizontal distance. Having gotten numbers for the path, I simply compared them to what I calculated from the formulas that I derived. That way I could find out if I had left a factor out or gotten a sign wrong or made any kind of error. And I was able to debug my math. Now, this is what's called a central force problem, where the force depends only on the distance from the center. And a very important concept in situations like this is conservation of angular momentum. And angular momentum is formed by what's called a cross product. There's a right-hand rule where you combine two vectors and you get another vector, which is the angular momentum vector. So here's the formula. R cross P. R is a vector from the target to the incoming particle. P is the linear momentum vector. So it's the mass times the velocity, the mass times the rate of change of position. Now, cross products work on the basis of the right-handed coordinate system. So if you have x and you cross it with y, you get something that goes up the z. If you take y and you cross it with z, you get something that goes out x. And if you take z and you cross it with x, you get something that goes out y. Now, the key point is that angular momentum is conserved. That is, it's constant. It doesn't change with time. And we're going to use that. Now, the cross product is perpendicular to both the vectors that get combined. So that means the angular momentum vector is perpendicular to the plane of the experiment. It always points in the same direction. So we're going to just deal with the magnitude, the signed magnitude. Now, with a little geometry, you can derive this formula right here. The magnitude of the angular momentum is the mass times the square of the distance from the nucleus times the rate of change of the angle. The dot over the angle, over the theta, indicates the derivative with respect to time. And I'm going to have a double dot for the second derivative. So if you substitute this in, then you can show that the angular momentum doesn't change with time. Now, theta is the angle from the nucleus to the alpha particle. Now, the nucleus is like here, and the alpha particle's coming in this way. And so the angle is actually decreasing with time. So the magnitude, the signed magnitude of the angular momentum is negative. And if you look at the geometry, you can see that when the alpha particle is far out at the beginning of the experiment, the cross product only involves the velocity of the alpha particle and the distance, the vector that I've shown in blue here, the impact parameter. And since they're perpendicular, the cross product just gives you the simple multiplication of the two. So the angular momentum at the start of the experiment is the mass times the initial speed times the impact parameter with a minus sign. And that's the initial angular momentum, but since it doesn't change with respect to time, that's the angular momentum throughout the experiment. Now we're going to get to the main point of this exercise, which is to solve Newton's second law of motion and get the path of the alpha particle so that we can compute the scattering angle, the angle at which it flies off. Now, what I've shown here, equation 19, it's the radial acceleration with the radial force. And This is Newton's second law of motion, F equals ma, in polar coordinates. And so we've eliminated the theta, the polar angle. The second term, the L over mr cubed, sometimes called centrifugal force, although it's not really a force. Now, to make the math tractable, we have to do a transformation. We have to go from the radius to the inverse of the radius, which I've given in equations 20 and 21. Substituting them and multiplying by minus m over L squared times u squared gives you equations 22 and 23. Here's another figure indicating the initial angular momentum when the particle is far out. So by substituting this inverse radius relationship into Newton's second law of motion, you get equation 24. The second derivative of the radius with respect to the time is proportional to the second derivative of the radius with respect to angle, with a proportionality factor and a minus sign. Putting that into our Newton's second law of motion, into equation 19, and multiplying by minus m over L squared u squared, we get equation 25, which might be familiar to you. It's basically the formula for the motion of a spring, of a mass, hanging on a spring. And so it's an oscillatory solution. The solution involves the cosine function, and there it is in equation 26. That's the solution to this equation. And our next task is to show that this is a hyperbola, and furthermore, we have to determine these constants, because this is a general solution, but we don't know A, and we don't know theta naught. We have to determine them. Well, there's a few things we can notice. Have a look at this figure. You can see a few things. One is, at the point of closest approach, the alpha particle is always ahead of the gold nucleus. It never gets behind it, really. And the scattering angle is anywhere from 0 to 180 degrees. And there are some other things we can determine by looking at this figure as well. Suppose the angle at the point of closest approach, periapsis, is called alpha. Then it's within 90 degrees of the angle to the alpha particle. You can see that from the figure. And that means that the cosine is positive. And what that means is that we can choose theta 0 to be the point of closest approach. Because when theta equals theta 0, the cosine is at a maximum. The inverse radius, is at a maximum, so the radius is at a minimum. Another thing you can see is that for the radius to be positive, A has to be greater than mk over L squared. K, by the way, is the force constant. It's the product of the charges of the two particles divided by a proportionality factor to make the units come out right. So, like I say, our next task is to show that it's a hyperbola. And what I'm going to do, I'm going to take the definition of a hyperbola, and I'm going to use a theorem from high school geometry, the law of cosines, to show that it satisfies equation 26, the differential equation for the inverse radius as a function of angle. So the definition of a hyperbola is you have 2 points. These are called foci. One here and one here. This one is where the nucleus is, and this one is sort of the mirror image of it. If you look at the distances to the alpha particle from these 2 foci, the difference in the distances, you subtract the smaller from the larger, you always get a constant no matter where you are on the path. In this figure, the difference is 4, but it'll be different for our problem. Now, the law of cosines, you can see I've got a triangle here. So I've just drawn that triangle again here. And I've got 3 sides, A, B, and C. And this angle here, which is the difference between the angle it would be at periapsis, at closest approach, and the angle it's actually at. So it's theta minus theta naught. Here's the law of cosines. It's kind of a generalization of the Pythagorean theorem to take into account the fact that it's not a right triangle. If you apply that to the triangle I just showed you, you can show that 1 over r, that's u, the inverse radius, is equal to a constant, a negative constant, plus a multiple of the cosine function. Well, this is exactly the form of the solution to our differential equation. So I've demonstrated that a hyperbola satisfies the equation, and in fact, A and epsilon governs the shape of the hyperbola, because you can have a hyperbola that's almost straight, or you can have one that's scrunched down like that, and epsilon controls that. A is half the difference between the 2 radii, so that determines the scale of the hyperbola. And equations 28 and 29 give the correspondence. On the left of the equal sign are the parameters of the solution to our differential equation, and on the right are the parameters from the definition of the hyperbola. All that remains now is to determine A and theta naught. You can show by a trigonometric identity, you can show that A times sine theta is the square root of A squared minus U plus K squared. Likewise, you taking the derivative and applying the chain rule, you get this relationship right here. Now, initially, the rate of change of U is minus 1 over r squared times the speed. And so that gives us minus the square root of A squared minus kappa squared theta dot. Kappa, this is kappa right here. Solving these equations, we get the scattering angle is equal to pi minus 2 times the arctangent of the mass times the velocity squared times the impact parameter s divided by the force constant. The force constant k is the product of the 2 charges divided by a proportionality factor designed to make the units come out right. Well, by a trig identity, you can get that the scattering angle is 2 times the arctangent of the angular momentum. Remember, the angular momentum is the same at the end of the experiment as at the beginning. The angular momentum divided by the mass times the initial speed squared times the impact parameter. Well, this is the principal result that all the textbooks have that I set out to prove. Now, if you liked this video or found it interesting or helpful, click the like icon, enable notifications, and I've also included a link to the slides, to the document with all the equations in the description below. So, as I said, you don't have to take notes. If you're curious about the details, you can download the math and have a look at it. Thank you for joining me, and have a good day.